So we're going to, in 6.3, be looking at the situation where we can have a forced harmonic oscillator where the forcing function itself gets turned on at a certain point in time, or, if you wish, turned off at a certain point in time. And we can make things a little bit more complicated if we wish. But we're, in this case, fusing chapter 3, which is harmonic oscillator stuff, with chapter 4, which is the forcing function attached to a harmonic oscillator, and now with chapter 6 stuff, which is all about the heaviside function and, if you want, Laplace transform stuff. So 6.3 really kind of ties together the last couple of chapters that we've had and gives us a chance to practice all of that. And so that's what you're going to be doing here in a moment in the classwork for 6.3. In between that and the kind of the second half today, what I'm going to do is I'm going to do a little show and tell. I'm going to show you my version of a solution for the one of the tasks, the final exam tasks that nobody picked. So I took one of the ones that nobody picked. I just grabbed the first one, which was number 1. And I came up with a solution, and I have not looked at it since I came up with a solution, so I probably should refresh my memory while you guys are working on 6.3 classwork. And then I'm going to present that to you and kind of do my little demonstration of what am I looking for when I say a presentation of the solution for one of these tasks. I just wanted to give you a feel for what I mean. And it also hopefully will assuage your fears, especially if you haven't started looking at the tasks. I don't think any one of the tasks is really super detailed, but you're going to have to put some thought into it, especially answering some of the questions. A lot of it is stuff that you can do in Maple, but unfortunately, a lot of it is not stuff that Maple is going to be terribly helpful for, like being able to interpret the context of a differential equation or talk about what the variables mean, stuff like that. Maple's not good at that, but Maple's really good at creating visualizations and solving things. So that's important. So I'll do my little show and tell, and then the last chunk of class will be a chance for you guys to work on the final exam tasks of your choice. You can also use that time to work on homework, which is a little bit more pressing because that's due on Wednesday. So game plan is today we're going to finish up 6.3, work a little bit on the final exam tasks, and then on Wednesday you will have turned in your problem set, and in class on Wednesday we'll be doing review for the final exam, and the final exam will land in your lap after that. The solo part of the final exam will land in your lap after that. And then you'll have the weekend to finish that up. And on next Monday, a week from today, you'll be presenting your solutions for your team tasks. So pretty good. Okay. Makes sense. Any questions, logistical questions about, wait a minute, what about this? How are we going to do that? Anything about that? No. Emma, you alive? Steven, you alive? Everything okay?
Yep.
Excellent. Cool. I just wanted to make sure. Emma's like, thumbs up. Okay, cool. So what I'm going to do right now is get you guys broken up into the breakout rooms. And because Austin said that he will be here, he promised me he will be here, I'm going to make a breakout room for that group. I think I still have, so hold on. Oh, wow, that's weird. It had, oh, that's crazy. It still had the, oh, that's because sorry. 5 rooms manually. I'm like, wow, this is like the rooms from last time, but it's not. Hold on. So, Matt and Stephen are in that one. Next one is Paul and Crethany. Paul. I'm telling you, change your name. You want to have like a rock star name, Crethany? Nobody has that name. You would be unique. You could go by just one name.
There's a reason nobody has that name.
Oh, come on. John and Bryce with the next one. Let's see. Emma and Austin. Of course, Austin's not here yet. Okay, so I'm going to open up the rooms. I'm going to give us, well, I'll be poking around and stuff, but I'd say let's shoot for 30 minutes being able to come back. And that's, everybody's working on the same problems, number one and number two. The idea is I want you to work through those solutions. Yeah, so 30 minutes-ish, and then we'll check in and see how things are going. I'll poke around. If you have a question, you know how to get a hold of me. So there are the rooms. Defend yourselves. Okay, so we're back. So what we're going to do is we're going to take a look at the 6.3. There's only 2 questions, and it was really, the first one was about practicing the skill of the Laplace transform method for solving a great big second order differential equation. It's really solving a harmonic oscillator modeling problem, right? So anybody want to take it and show us what you got in terms of your work to support your answer? And then we'll have somebody else verify it with a quick desolve.
I got it.
Okay.
Hang on a minute while I share.
Oh, hold on. Did I already make it so?
Yeah, it looks like.
Okay, I did. Okay. I thought I changed the default settings earlier, but sometimes it confuses me.
Okay, so with number 1, it was really pretty simple. We just took the Laplace of both sides. And since both the initial conditions were 0, we were just able to go to the S step. And so we made s squared plus 4 times the Laplace transform y equals, and this side we used one of the tables to change from cosine t to this. And then we just solved for the Laplace transform y, which was
and
this
the 3
divided.
and the 3 there is just along for the ride on the right hand side. So
we just outside this. And then we solved for the Laplace transform y, which was this divided by this, which got us this. And then we par fracted it on Maple, and we got s over s squared. Well, that you see there. And so from that, we used the tables again and came up with cosine t y of t equals cosine t minus cosine 2t.
ding, ding,
So
ding.
it's pretty straightforward.
Yeah, pretty straightforward. So here's a question for you. Given the harmonic oscillator setting, if I told you this was a harmonic oscillator, what can you tell me about the oscillator based on the equation that we start with? So based on the original differential equation, what can you tell me about the harmonic oscillator?
There's no damping.
Yeah, there's no damping. So how does that manifest in the particular solution? How can you tell there's no damping?
Those the solution, it never changes amplitude. It's always going to be the same.
Yep, you've got 2 cosines. There's no involvement with any exponential decay. It's just cosine functions. This is a harmonic oscillator that's forced, but it's not in resonance. So, ta-da, a non-resonating harmonic oscillator. Ta-da. So nice work with number 1. Quick, hide number 2 before people have a chance to see it. So any questions on number 1? Can anybody verify that with a quick Maple desolve? Did you already do it? If you did, share your screen so we can see it. Or share a picture of your truck. That works too. Or share a picture of your face staring at the screen. You're all doing that. It's so weird, Emma, to have you there and not lagging. And I know, and you're just like, and you don't move and freeze in place. That's great. Do you have a microphone?
Yeah, I have my mic. I wasn't sure if the computer one was working okay, or if I should
Yeah.
put my headset one on.
Do you have Maple on that computer?
I don't, but I have my other computer right here. So it's like dual monitors except laptops. So
That's cool. Does it check out? Does our solution check out? That
yeah,
came
I think
up with?
so. That's what I got. I was just doing it real quick on some paper. But.
Cool. Anybody else check it on Maple with a desolve?
I'm working on it, but I must have goofed up somewhere.
Oh.
I started to desolve it, but I trust Paul's work, so.
Oh, because we all know if Paul doesn't get what Paul
It's giving me
wants.
an error, so I'm not sure what's going on.
Anybody want to desolve it? Anybody at all? All the other students sitting there staring blankly at your screen. Quentin steps forward and says, I can do it. So he did a quick desolve, and notice he's got desolve in brackets, the entire differential equation, and the two initial conditions, and it looks like, ta-da, looks like it's the exact same thing as what Paul got. And, might I add, the exact same thing that Quentin got. So nice work. And, oh, and you even plotted it for us. That was nice. That was good. Yeah, I want to see the plot.
Okay.
Because Paul's prediction was we have something that never changes amplitude. And I would say that's mostly right. Right? So taking a look at the plot that he has, you can see it doesn't change amplitude in terms of the maximum to the minimum range. It never gets higher or lower than that maximum or minimum. But it's actually a little bit more complicated plot than a standard wobble, 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 periodic function. So this is going on. So this, if you were seeing this as a harmonic oscillator moving back and forth, you'd see like, it would be a really interesting oscillator to watch. And if you've ever played around with, things, on springs and kind of played around with them, you can get really interesting periodic motion that is not simple. That's not just a standard sine or a cosine curve. So one of the ways you can do it is by tapping at just the right frequency, right? So if, here's the big dramatic finish for this one. If, Quentin, we wanted to adjust something in our differential equation, I want to change one number in your desolve up there, and I want to show that this thing goes to resonance. What number could you change to make this thing be in resonance? There's actually two numbers separately that you could change one at a time, but which one do you want to change?
Good question.
Yeah, it's like I come up with these on purpose or something.
I think it's this one, the 4.
Okay, what would you change it to?
Does that something to do with the inside of what's over here?
You're
So
on
like
it.
square root one way or another.
One way that, well, try it. See what you get.
So just that, I guess.
Okay, well, you're going to have to make it something.
Make it something.
Okay, go for it. Let's see. Oh, that's a pretty good sign, isn't it? So you can just grab the right-hand side of that puppy. Yep. It's heading towards resonance. So good job. So I said there's actually two. Yeah, lovely. There's actually two numbers that he could have changed. He changed the spring constant. What's the other number that he could have changed in his harmonic oscillator equation? It's forced harmonic oscillator equation. What other number could he have changed?
The mass?
Yes. You know what? I didn't even think about that. Yes, he could have changed the mass. Yep. So go back and change it. Make it 4, the way it was before. And what would you suggest, Paul, that we throw in front of the second derivative?
Oh, just say 5, I guess.
5? You just spitballing?
No idea.
Okay. Well, let's try it. We have an idea of what a solution would look like if it's in resonance. What do you think? Is that in resonance?
Nah.
No, and the key is it's got two terms, so it's not quite there. How about you change that 5 to a 4?
There it is.
Do you see the difference? It's a sine function times t. So you wind up with literally oscillation, but with an amplitude that is growing at a linear rate. And just to be cheeky, there is one more number that I could have changed. So yeah, get rid of the 4. There's one number that I could have changed, and Quentin was right on the verge of talking about it. What's the other place that I can fiddle around with?
Is it the inside of the forcing function right there?
Absolutely.
Maybe 2?
What would it be? Hey, all right. Throw a 2 in there and let's see what we get. And what do you know? We have our harmonic oscillator is again in resonance. So that tells us that resonance happens, remember, just recapping chapter 4 here, resonance happens when you have basically 0 damping, and the magic of the natural frequency, the left-hand side, the frequency of the left-hand side matches the frequency of the forcing function. And you can adjust the harmonic oscillator, change the mass and or the spring constant to make it have a particular natural frequency, or you can adjust the forcing function and change that side of the equation instead. So how I managed to get to all of that just from problem number 1, I'll never know. Okay, how about number 2? What was the hard part for number 2? Anybody want to take a stab at A? Walk us through your process.
We will volunteer to take a stab at A.
Royal we.
We will.
Proceed.
All right then. We'll...
Oh, he's just making that up. He's acting like his internet connection's all buggy.
Me?
It sounded like you went, At least to me,
enough.
it sounded that way. But go ahead.
I do tend to have buggy internet, but then I'm never aware of it. So our upload is it's quite a bit worse than our download, so I never notice it. But that's neither here nor there. It's all here, actually.
It's all somewhere else.
Yeah. So we started off with their normal classic oscillator stuff.
Yep.
Just decided to not bother with the constants because, why bother?
Why bother?
We figured out that that's our driving function, but it only turns on after 10 seconds.
So it turns on at 10 seconds. That's why it's a standard heavy side. Means before 10, it's off. After 10, it's on. Exactly. And after 10, it behaves like?
The heavy side or the whole thing?
Well, the right-hand side. After t equals 10, it behaves like?
Just like this. Oops, that's not what I wanted. It behaves like all that stuff. Because this just goes to 1.
Okay.
All right.
And then how did you find the other 3 parameters here?
So we played around with a bunch of stuff. We found that M is equal to 2.5 because that's what the problem said. B is 2.1 because that's what the problem said. K was a little bit tricky because you did a bunch of unit burying and messing around and mucking everything. But we were able to fish it out by taking the force divided by distance.
Okay, so walk me through. So the numbers there mean what?
So let me see if I can share this thing real quick. Take this maybe, and then take it right here and put it right there. And
it's 7 o'clock.
7 o'clock, guys. In case you want.
Hey, thank you.
Thank
you, Siri.
I aim to please.
I wasn't thanking you. It's all Siri.
Oh, well, I told her to say it, so
Oh, that's
all right.
deep.
So is that visible enough?
Yeah, that's good.
All right, sweet. So where is all this fun stuff? So right here is where we got our K value from. 34 centimeters with a mass of 121 grams is made to hang from it. And so what that means is that we get to, our force is going to be this mass times the acceleration of gravity, which is 9.81. But also our mass is in grams, so we had to throw that in kilograms first. And then to muck even more, our distance was in centimeters, so we threw that into meters. And then we just pressed enter, and we got this fun number.
So real quick, how come you use 0.121 and not 2.5?
What do you mean 0.25?
2.5. At the beginning, it says a 2.5 kilogram cart.
because that's not what we were using to calibrate the stuff. We
Okay,
didn't know
so
that this is this. And also
in
that's
other
not
words,
straight down.
yep. In other words, the K value is determined kind of as a side project. So the K value is, hey, I've got this mass, I hang it, and I get this sort of reaction from it. I can determine K from that and then use it in the regular problem. So
Shouldn't the mass be the mass of the cart plus the mass of the fan, the 2.5, I mean?
good question.
2.688, I think it was.
Were we given the mass of the fan?
Yeah, it was
Oh, yep,
0.188 or 188 kilograms.
I think it would be, is it
Oh,
0.188?
you're right.
Yep.
I missed it. Period. There we go. All right then. So then we declared the heaviside function, just because that's kind of important. And we got this lovely equation.
Holy cow. So before you go too far into the incredible number of, oh yeah, it even involves a Dirac delta function. Wow, that's lovely. But of course, we don't really care about the form of it. We're not going to write that down. That's not important. We're just going to use that to make sense of our solution, like to make predictions. But before we do that, can you scroll back up? So the right-hand side of your differential equation is 0.3 sine 0.0 or 0.4t times the heaviside function of 10. So what that tells me is at t equals 10, suddenly the switch gets flipped, right? And this thing is turned on and it starts behaving like whatever 0.3 sine of 0.4t would have been at that moment in time. As opposed to, and see if you can hear the difference, as opposed to at t equals 10, the fan turns on and it immediately starts behaving like 0.3 times sine of 0.4 times whatever time you're at right then.
Mm-hmm.
In the first case, it's like 0.3 sine of 0.4t is sort of running in the background, but it's just ignore it, ignore it, ignore it, ignore it. And then you get to t equals 10, and then it starts behaving like the sine function. But it kind of starts behaving like it at whatever point in time you turn on the switch. As opposed to there's nothing going on, and then as soon as you reach t equals 10, it turns on, the fan turns on, and it starts behaving like that sine function, but over here now at t equals 10. So my question is, where do you see in the problem, in the actual text, which one of those is correct? Where do you see the text that leads you to your conclusion as opposed to the other conclusion?
Is it because of the magnitude thing?
Say more about that.
I was just looking and like it just says, it doesn't say, it just says that the magnitude of like the force that the fan creates is going to be equal to that sine curve. It doesn't say that it follows it exactly, just shifted. I don't know if that's,
So you're saying, based on your reading, that it should be or it shouldn't be a shifted switch?
that it shouldn't be a shifted switch,
Shouldn't be. Okay.
I think.
Well, let's try it. Can we try it two different ways, maybe? Try it this way and then try it the other way and see whether there's a significant difference in what we get in terms of the prediction. So you've got an equation just using the formula that you've got there. You can kind of solve for this equation EQ. What would it look like if it was a shifted switch situation? what would change about it, I guess is what I'm asking.
It would be 0.4 times t minus 10 in the sine function, right?
That would be what we'd have to change. In other words, it would be saying it's going to behave like this 0.3 times sine of 0.4t, but shifted to the right 10 units. So it's going to behave like this sine function, but shifted to the right. So here's the question. Let me approach it a slightly different way. How could you phrase it in the problem, in the question, so that it clearly means shift it over 10 units? And this is general for other people. Steven's working on putting stuff together here. So, and by the way, you'd want to have the t minus 10 in parentheses inside there too. So, getting dizzy.
Like that?
Yeah, one more parentheses on the end. Yep. There you go.
I gotta restart the thing.
So other people enjoying the anonymity of silence. How do you think you would go about changing the text of the problem itself to distinguish between shifted switch or not a shifted switch situation? Aside from saying this is a shifted switch situation. And that would be the obvious way to do it.
Well, couldn't you say, like, if you carried on that last sentence, so if you said the direction of the cart's motion is equal to 0.3 times the sine of 0.4 t, where when t equals 10, that function is equal to 0, because that would be the starting point of a sine curve normally.
Yeah, that would be getting at it. This idea of you could just say comma where t is the starting of the fan, right? Does that make sense? It's a problem. This is a problem because there's a kind of a level of abstraction there in the language where we have to be able to describe at what does it mean to, what does it look like to have a shifted switch situation where the thing turns on and it behaves like the function but shifted over. How do we say that in English without coming out and saying it behaves like the function this but shifted over, right? It's a little clunky. Mathematically it's very elegant, but in English, it's kind of clunky. Is it safe to say that the two different equations are going to produce two different results?
Not so much in the long run, right?
Interesting. Say
We
more
just
about
kinda
that.
like, it's like once t equals 10, it would either jump up or stay where it is, or like it would jump a little bit, but then after a while, it would still be oscillating.
So maybe we can plot the solution for both of these? Did you eventually further down, did you plot the curve? Yeah, okay, cool. So if we just turn this thing on and then let it run for, I don't know, let's go t equals, we don't need -10, but let's go all the way out to, I don't know, call it 500, just for giggles. Let's see what we get. So now, is there a way we can produce the y of t for the other equation and plot that and see what that gives us?
I'm not sure. It took me quite a bit to play around with all this stuff to get here.
That makes sense. But if we were to try plot, and then inside that, the right-hand side parentheses desolve. And now you're going to desolve whatever the equation SS, right? Comma y of t. Yep, you got it. I don't think you need the y of t though. You just need you'll need the brackets around. Yep. Then close your bracket, and then close your parenthesis, and
Maybe
then
one more.
yeah, that should give us a plot of the right-hand side of it. Uh-oh, what's going on? It doesn't like right-hand side of that. I'll tell you what, instead of EQSS, just scroll up and copy copy the output. Or that works too. Yep. My worry is that it's too many layers of. There you go. Okay, what's going on? Indication of the solving variable for the given system.
You're gonna need
So-
to want stuff.
Is y of t a declared variable?
Oh yeah,
It
it is.
You're
It
right.
is a
Let me
declared
just-
variable at this point.
We'll just kind of.
Fudge it unassigned. There we go. Try it again.
Nope.
Oh, that's not the problem. Oh, it's not
Isn't
yet
like the
handling.
Heaviside stuff.
Oh, parentheses, the multiplication before the Heaviside function, maybe. Oops.
Missed. Doesn't like the Heaviside function itself.
Case split. I don't know what that means. It's not handling the function. This is one of those moments where I'd be like, okay, just delete Heaviside t minus 10 and then back it up and then type it in, because it's almost like it's not reading it as a function. So yeah, just delete that and now type in. Yep. And then parentheses t minus 10. Let's see. Wow, I don't know what it's doing.
It didn't let me desolve a Heaviside function earlier when I tried it.
Really?
I had to do a bunch of Laplace stuff.
It should not be a problem for doing a desolve here.
Yeah, let us desolve it.
Yeah,
Maybe I should restart my Maple.
maybe. I mean, here, let me see if I can.
You want to share yours, Chris?
I can do that. All right. So what were we on? B or?
Yeah, just trying to get a plot of the second way with a shifted switch.
Okay. That would be it, right? Just adding the sun.
Yeah. Let me get my maples on the way here. Hold on. So notice the graph looks a little different. But
Go back, there's Control Z, and I can go back to the other one.
yeah, the graph looks a little different. But in the long run, the argument is this thing is going to behave exactly the same. You've got a damped harmonic oscillator with a periodic forcing function. After it turns on and you wait long enough, the natural part of the solution goes away, and you're just left with the steady state part, which is just the heavy side, or excuse me, everything after the heavy side turns on. It's just a periodic function. So sorry we're having maple troubles on that one. It shouldn't be giving you nearly as much of a headache. I don't know why. But the argument would be, in the long run, it doesn't matter whether it's a shifted switch, heavy side, or a non-shifted switch, heavy side. But I would say it makes more sense to talk about as soon as the switch gets thrown for turning on the fan, it behaves a certain way. Think about the physical reality of what we're talking about here. If you have a fan that's sitting on top of your cart, and so imagine, here, let me draw on your screen here for a second, Chris, if you don't mind.
Not at all.
Okay, so imagine that we have if I can draw. Oh, I don't need to draw with that big of a marker. Oh, what the hell? I'll draw with that big of a marker. Let's say you have a cart, and on top of the cart you have a fan. And this is how exciting my fan is, right? But the fan is facing sideways towards us, right? The moment it turns on, and if you imagine that the cart is moving in this direction, but the fan is pointed out towards us, how much of that fan blowing is going to contribute to the motion in this direction? Hopefully, it doesn't take tons and tons of vector physics background to know that if your fan's blowing this way and your cart's moving perpendicular, then none of that fan blowing is going to make a difference. So that would be the equivalent of starting off initially with zero force due to the fan. But as the fan rotates and it spins around and starts to point in the direction of the cart, as soon as it gets to there, then it definitely will affect the motion of the cart. So as it starts to spin, it has more and more of an impact on the cart. And this is why there's this periodic, that's the sine part of it, right? Because sometimes it's pointed perpendicular to the motion of the cart, sometimes it's pointed this way, sometimes it's pointed exactly opposite, so it's kind of pushing in the other direction. So if you think about this forcing function as contributing to the motion of the cart, it does sometimes. Sometimes it contributes a great deal when it's pointed along parallel to the motion of the cart. Other times it contributes nothing at all when it's pointed this way. If a sine function starting at t equals 0, what direction does that mean the fan must be facing? If its forcing function is a sine function, sine starts off at an angle of 0 with how much contributing force? When t equals 0 in that forcing function. You know, if you ignore the heavy side part of it for right now, but at t equals 0, 3 times sine of 4, or 0.4 times 0 is how much? This part right there. This is incredibly frustrating. I don't know if it's because you don't know what I'm asking, or you're lagging, or because you've secretly snuck off and are trying to figure out how many countries there are in the world. That's a very motivating question, I know, but help me out here. What's What's a better way to ask this that might motivate you to say something?
Could you rephrase the question?
Sure. If I write down, if I type in here, let me do this. If I can type in, there we go. If I type in, this is my function for sine 3t. If that's the function that my fan is contributing to the motion of the cart with, at t equals 0, how much is the force contributing to the motion of the cart?
0.
0, because when t equals 0 in that means that there's no force at all, which tells us that we must have a situation where the cart's going this way, and at t equals 0, it must be pointed exactly perpendicular. In other words, it's not contributing to the motion of the cart. And as time goes by, it starts to contribute to the cart's motion. And then eventually it points back perpendicular and it goes back to 0, because that's the way sine functions work, right? So as this thing rotates, as the fan spins, as it oscillates, you wind up with sometimes the fan contributing quite a bit, sometimes the fan contributing not at all, because it's perpendicular to the oscillator. Does that make sense? Did that help, Stephen, in terms of rephrasing?
Yeah.
So then my question to you is, does it matter whether we have a shifted switch situation or not in terms of what happens when t equals 10? Because if I plug in t equals 10 to this guy right here, that 4 times, I'm just making up the numbers, 4 times sine of 3t, that is not equal to 0 when t equals 10. But yet the fan is not on up until that point, so it's pointed perpendicular to the motion of the cart. So it does not make any sense to ask the fan to suddenly like jump to a place where it's pointed non-perpendicular, right? The shifted switch serves the purpose of making the math fit the reality. The fan is pointed perpendicular to the motion of the cart, and it's off until exactly t equals 10 seconds, and that's when we turn it on. And at that moment, it's not contributing any force along the path of the cart. But if we don't use the shifted switch, it would be contributing along that direction, because the clock is running, the clock is running, the clock is running, and then at t equals 10, that doesn't correspond to perpendicular in that equation. It corresponds to some contribution.
So in this specific problem, the way it's worded, is there anything that gives us a definitive answer to whether it's a shifted switch or not?
So looking at the problem, you'll notice it says after 10 seconds, additionally, a small oscillating fan is attached to the cart but is initially off. After 10 seconds, a small fan turns on and begins to oscillate, creating a forcing function whose magnitude along the direction of the cart's motion is equal to this. The way it's written, on purpose, there's no way to know for certain whether it's that t in that forcing function that I give you is time from the beginning of the problem or time from switch turns on for the fan. On purpose, I did this because I wanted to have this discussion during the classwork. And so when I said earlier, what could I have done? How could I have rephrased things to give you a little bit more of a hint as to, oh, the fan is off, but it's perpendicular. So one of the things I could have told you is the fan starts off pointed along parallel to the direction of the cart, right? And that means that whenever the fan turns on, it instantly has to be at its maximum contribution, right? And so cosine function at when t equals 0, that is along the maximum, right? Because cosine of 0 is 1. Sine of 0 is 0. So sine would be perpendicular, cosine would be parallel. And then if I were to say it has this form of this function and it turns on when t equals 10, that the only other way that I could think of would be to add a little caveat at the end of, as we were saying earlier, where you say comma, where the t in this equation corresponds to the t equals 0 corresponds to when the fan gets turned on. Okay? Or you could have used a slightly different variable. You could have said t sub a, like when t sub a equals 0 is when the fan gets turned on. So it's subtle, but it's super important to the immediate effect of the fan, even though we all agree in the long run, this thing is going to behave like a periodically forced damped harmonic oscillator, right? Snooze, boring. But in the immediate short term, it definitely behaves in a particular way. And it's different if you have a shifted switch situation than if you have a non-shifted switch situation, just a standard Heaviside function.
So basically, this minus 10 next to the T is just the position, like, of the fan. Like making sure the position stays.
Yes. So basically, it's a guarantor that the fan in its initial position doesn't turn on and doesn't start to do anything until t equals 10. And then at that moment, that's when it starts to behave like the sine function. It's just shifted 10 seconds into the future. So I'm curious, because we've got your maple up. Can we take a look at what you did for part D? After 30 seconds, the fan's batteries are depleted.
All right. So we said you need another Heaviside function to kind of like turn it off.
Okay.
And so since this one isn't going to take in any effect until 40 seconds.
Now, why is it 40 seconds? You're right, but why is it 40 seconds?
Well, originally we said 30, but then we read it closer and it said that the fan runs for 30 seconds.
Yeah.
So if it starts at 10, it's going to end at 40.
So do you see all the little places where the language kind of, it translates very reasonably into an equation. The equation makes sense, but connecting it to the physical reality and the description of the physical reality, that's the hardest part on these problems. Guaranteed. Right? I promise you there will be a problem like this on the final exam. I promise you I will try to trip you up with funky wording, right? So read carefully, think about it, and see if you can make an argument for one way or the other. Right? So nice. So you've got the 1 minus Heaviside. That's a way of having it be on to begin with, but then turn off at whatever that time is.
Right.
So cool. And then for part E, describe what you expect the plot of the modified IVP solution curve would look like. So what would you expect it to look like if the fan turns on at 10 seconds, turns off at 40 seconds? What do we expect it's going to happen to the position function for this puppy?
We said it would go to 0 because there's damping in the actual problem.
The forcing function goes away at 40 seconds, and there's damping. So, in the long run, this thing is just going to stop. So,
and then we did a desolve to test it.
And what'd you find?
It did exactly that.
Hey, what do you know? Look at that. And you can see at t equals 10 seconds, that's where the fan turns on, and it starts to head towards a nice, consistent, long-term solution. Then we throw a spanner in the works at t equals 40. That's where we kill the fan, and it just quickly just kind of dies off. And the oscillator stops. It heads towards rest. So nice work. Good job. And you verified it. Okay. Everybody needs to take like a 30-second stretch. Stretch. Come on, stretch. Everybody stretch. Everybody stretch. Come on, Quentin, stretch. John. Come on, there we go. Yeah. Austin, stretch. Stretch, Austin. Stretch.
I already stretched.
Okay. Are you ready? Are you ready for t Team Tucky. Okay. I'm going to hit pause on this recording, and I'm going to walk through my solution, my attempt at a solution,